This is my screencast for chapters 3 and 4 for the online quantum class. Let's start with the photoelectric effect. The basic idea here is that if you shine light on metal, electrons can come off. The model that I like to have of electrons in a metal, there's of course two different kinds of electrons. There's the ones that are very tightly bound to the ions, and then there's those last few for every atom that are free to roam. They're in the conduction band, it's called. I like to use the analogy of it takes a village to raise a child, or if you think about like a block in your neighborhood, if you knew all the parents in your neighborhood, you'd let your kids, your older kids who are, sort of mature and able to roam around, you'd let them roam around. And since you trust all the other parents on the block, it's not a big deal. And so I say that the electrons in a metal are free to roam, and just those conduction electrons, the mature kids. But you usually lay some ground rules down. You tell your kids they can't cross certain streets in your neighborhood, and the same thing goes with metals. They can't just leave. If they were to get too far away, there would be a net residual positive charge left behind that would attract them back again. And it doesn't have to be their original parent ion. It can be any of the ions nearby. It would essentially present a net positive. So the basic idea of Chapter 3 is that light can provide the energy it takes to escape. So it takes energy to bust out, to cross that street, and so light can provide that energy. There's this really nice simulation software from the Colorado people, but it appears to slow the screencast down, so I'm not going to click on it. I would recommend that you look at it here. The basic idea is if you shine light on a metal, and the electrons can escape, that's all fine, and they can maybe drift over. They'll have, if you give them 5 units of energy and they got to waste a couple of units by escaping, they still got 3 units of energy left. They can sort of fly in random directions. If you put a collecting plate nearby, well, okay, maybe a few will fly in that direction. The problem is that plate will eventually become negatively charged. And so eventually the electrons won't really want to go there anymore. The question is, what will it take for an electron to head towards a plate that's already negative? Well, if it has enough kinetic energy, it can sort of burrow its way in, even though all the other electrons are saying, go away, go away, go away. If it has enough energy, it can go through. So when that plate reaches its final charge or final voltage, you get a sense, in other words, it's not changing anymore. No more electrons seem to be burrowing through. You get a sense of the maximum amount of kinetic energy that electrons could possibly have when they're leaving these metal. So we have this wave model, and there's several predictions. I've got this equation that's also in the book. I'm just going to slowly go through it. We want to figure out, one of the big deals is how fast the electrons would be ejected. Well, electrons ejected per unit time. You need to know how much energy each electron gets, and of course compare that to how much energy it needs and in how much time that happens. So the energy delivered per time and per area, and multiplied by the area of each electron, let's say the area of an atom, and then the energy needed per electron. Oh, looks like I'm missing a parenthesis there. And what you realize is some pretty straightforward things here. If the intensity is increased, if you have more light shining down on this, these sunbathers, I consider the electrons to be kind of bathing in the sun, collecting energy until they finally get enough to escape. If you give them more energy per time, then more electrons will come out faster. How big is their body? They're collecting the sunlight here, and so if it's even bigger, then it can collect the energy faster. And of course it depends on how maximum security the jail that they're in. If it's a high security jail, it takes quite a bit of energy to escape, then it's going to have to sit there for a long time before it gets all that energy. So that's one of the predictions of the wave model. What are some of the other predictions here? These are the same numbers that are in the book. Well, at high intensities, you would expect more intensity, more electrons coming out. Right? You're giving more energy to the metal. Each electron needs a certain amount of energy to escape, and so you pour it on a little bit harder, you get more out. No big deal. At very low light intensities, though, there's this time delay. This delay, because if they're out there sunbathing on a cloudy day, they don't have a chance of collecting the energy. They're going to have to sit there a while before they finally get enough energy to bust out. So that's one of the major predictions of the wave model to explain this notion of electrons leaving metals. There's this issue of a very complicated connection to the frequency of light that you're using, because there's resonance effects. This explains why different crystals are different colors, for example. Well, that's crystals, and we're talking about metals here, but we actually would kind of expect something very strange to go on. And resonance is something that happens whenever waves interact with just about anything. So we actually expect very different things for the different metals. Now there's this notion of the maximum kinetic energy that the particles can get. That's this notion of, if you put down a piece of metal nearby, what is the maximum voltage that achieves? That's determined by the maximum kinetic energy these electrons come out. Again, if they come out with a lot of energy, a whole bunch of them can stick onto that plate, because even though that plate says go away, go away, go away, after a while, if they've got enough kinetic energy to sort of burrow through, they will. And so that maximum voltage that plate achieves is a measure of the maximum kinetic energy. Well, if you increase the intensity, what we actually expect is, during the time that it takes a little while for these things to get the energy they need to escape, and it takes a while to escape, in fact. If the intensity is super high, while they're escaping, they're getting even more and more and more energy, and so you would expect them to have very high intensity. The author uses this notion of big tidal waves versus just little tiny waves. You would expect the kinetic energy to be quite high if the intensity is high. Okay, so here are the facts. First one, just like we expected, more energy coming in, more electrons coming out. So the number of electrons that come out seems to be proportional to the intensity when the intensity is high. Big problem, though. It seems like as soon as you turn the light on, even if it's a wimpy little light source, the electrons are ejected instantly, right away, immediately. They don't have to sit there and wait and collect the energy they need. If you hold the intensity constant, that's what I mean here, and you increase the frequency, the number of electrons goes down. So we did expect something weird to happen, some very crazy resonances, but this is just a sort of a uniform thing that happens for all metals. If the frequency is too low, this is really new and interesting. Nothing happens. If you use low frequency, so long wavelengths, so something like red light, infrared light, radio waves, you can shine this thing on there forever. The electrons will never come out. If you hold the frequency constant and you increase the intensity, so you'd think, okay, well, it's going to be a bigger wave. You'd expect the kinetic energy to be higher, the maximum kinetic energy. Turns out the maximum kinetic energy doesn't seem to have anything to do with the intensity. It only has to do with the frequency, and that's what I've written here. The maximum kinetic energy is just plain old proportional to the frequency. We can see a graph of that here. Here's frequency. Here's the maximum kinetic energy you can get out of the thing. Maybe just a few different metals. Maybe just change a little bit here so it doesn't look so boring here. Maybe 4.3 or something. Let me resubmit that. Okay, so now these are different metals, all different metals with different work functions here. I just put in 4 different ones. Feel free to play around with this. The point is that the slopes of all these lines are the same. Their x-intercepts and therefore their y-intercepts are all going to be different. That's a separate issue. But the slopes are all the same. So it's just this kinetic energy maximum is proportional to the frequency. Alrighty. So Einstein comes along and he says, well, there's this photon model that might explain things. Well, what if we said that light actually was made of these little particles? Let's call them photons. And let's say that they have this energy, Planck's constant times frequency. Another way to write it, hc over lambda. And he says it's very simple. An electron either catches a photon or it doesn't. It either gets the entire photon, the entire quantum of energy, or nothing. If it gets it, of course, so here's how much energy it has. It has to escape, so it has to cough up some of that energy to breaking out. This is the work function. Whatever's left, woohoo, kinetic energy. Another way to write it, hc over lambda minus w. We get a lot of these hc's, by the way, and that's roughly proportional to 1240 electron volt nanometers. Electron volts are a very convenient unit of energy when talking about electrons, and nanometers are very convenient when we're talking about wavelengths. I want to know why we keep talking about the maximum wavelength. Let's scroll down here. I'm going to make this just a little bit larger. There we go. Okay, so here's a model of a metal. I want to make sure I explain this y-axis. This axis here is energy. Okay, so what we have is different levels where the electrons can live inside the metal. These are all sort of the free stuff here, the free to roam around in the neighborhood. And of course, nature's lazy. All of these electrons want to be in their lowest energy state, but why don't they all just pile up down here? Well, because electrons hate each other. You can get a spin up here, a spin down there, a spin up here, a spin down there, a spin up there, and a spin down there. But they pile down as low as they can go. Now, this line here is very important. This is freedom. This is what we call it, energy equals 0. If you can just get up to there, you're free. You can do anything you want. Right now, you're bound. You have negative energy. You're below this. So if a photon comes in and let's say hits this electron right here, it's going to, let's say it has enough energy to break free, and anything above is gravy. Then that's extra kinetic energy. But if that same photon hits this one, right, and who knows which electron it's going to hit, well, then it's going to waste even more energy before it gets free. That's why we keep talking about the phrase maximum kinetic energy. It's what happens with these electrons. But quite often you get all these other electrons too. So for the very same color of light, you get different kinetic energies. But you can get a measure of the very maximum one here, and that gives you a measure of what we call the work function. All right. I'm going to skip this section on detecting individual photons as photomultiplier tubes. Certainly read the chapter on that part. All right, so chapter 4, particles as waves. Well, first let's say, why do we even think these things might be particles? They're so esoteric. They are so strange. They're all these tiny little things. We have no idea what's going on with them. But we actually have a record of them being particles. Let's take a look at this bubble chamber here. We have magnetic fields and these red lines going up, which you get with coils. It's this liquid, I don't know, hydrogen or something. Excuse me, liquid nitrogen does the same. It's in a piston, so you can change the pressure. You optimize the pressure and temperature such that just the barest amount of energy will actually boil this liquid, make a little bubble. How do you get that energy? You put particles in. So these particles come flying in from wherever, and they leave bubbles wherever they are. The magnetic field makes them spin around in circles. So these are little tracks. I don't know if you can see them in there. And down here somewhere are really examples. Look at this. Here's a particle that's just spiraling away. Spiraling because of the magnetic field. Man, these look like particles. No question about it. But there's something else going on. So let's go to, I guess I want to be down here. There we go. I want to point out that page 63 has a misprint. Q4.3 has the numerators and denominators kind of screwed up. So this is what I have here, and the hyperphysics page is a lot better. Now you have to do some relativity to get this down. We're not doing relativity, hopefully, and we'll be doing that next summer. But the problem is, we want to understand what the momentum of light is. What does it mean to have momentum if these things are massless particles? Well, they're smacking you. They deposit energy on you. And that's just like a pressure, so it's like momentum. And you can relatively straightforwardly prove that the momentum is the energy divided by the speed of light. We know the energy, it's hc. And so you get this relationship that the momentum of a light particle is just h over lambda. You can solve this and you get lambda equals h over p. H over the momentum. All de Broglie said, all he did was he said, maybe that's always true, not just for light. And of course that leads to all kinds of crazy things. Excuse me. So we want to study these electrons. We want to give them a certain momentum and check to see if their wavelengths, whatever that means, is what we think. So we want to prepare an electron beam. So we have a simple anode-cathode set up, so just two parallel plates, let's say. And on one plate you heat it up, make it really, really hot, so that electrons just barely escape. You give them just enough energy through heat to just barely escape. They're just sort of, they escape, but they don't have kinetic energy to run away. Then the other plate, on the other plate, you make it positively charged. You do that hooking it up to a battery. Quite straightforward. And those electrons, which just barely escaped and were hanging around, they see that other plate and they say, woo, I'm going to go over there. So they run over there. Let's use the sides of this. Let's maybe use, where this dot is one side, and where this letter E is the other side. So they boil off, and they're going, oh, boy, that was nice. I've escaped. And then, whoa, look at over here. This is positively charged. I want to run over there. So they run over there. Imagine you had a big wall right here. They'd all smash into this wall. They're very excited to get there. Well, if you poked a little hole, maybe right where this letter E is, they can just run right on through. And so by adjusting this voltage, you can adjust how much acceleration they feel. If you adjust how much acceleration they feel, you can adjust their speed. And we know that kinetic energy is 1/2 mv squared. Another way to write that is p squared over 2m. It's a much more convenient way of writing it because p is related directly to lambda. So we get lambda is h over p, and here's a fancy way of writing p. The square root, why square root? Because of this square right here, of 2 times k times m. Well, I wrote it as e here. I suppose I should have written it as k there. Now, your author quite often likes to make sure that h is never alone. Whenever you have an h, it's nice to have a c. So, well, here's a lonely h. Let's add a c. If you add a c in the numerator, you got to add a c in the denominator. But because of the square root, you have to add a c squared. Well, that's actually quite convenient because mc squared for an electron is really easy to remember. It's 511,000, 511k, or 500,000 roughly. And that's easy to remember, and HC, recall, is just 1240. So then you can do your math a little bit easier. All right, so we have this Davis-Germer experiment, the very first experiment that did this. You shoot some electrons at a surface, bounces off, goes in some particular direction. You have, the book analyzes what happens with just a couple of dots, maybe say this one and this one. The Davis-Germer experiment, and maybe you've heard of this Bragg law before, actually calculates it for a whole bunch of particles that are very nicely spaced. The upshot is, if you treat it like waves bouncing off things, then you get some predictions of particular angles where you actually expect to see some peaks. And so this is, you get different peaks for different accelerating voltages. That means different wavelengths, and so different wavelengths peak out at different times. So electrons are waves, and waves interfere. Electrons must too. So can you do the double slit experiment with electrons? Well, you can, but the wavelengths are pretty small, so you have to have a teeny tiny double slit. Well, people have done this, and I think this is just a great photograph on page, it must be 69, Q4.4. So take a look at that. Very interesting, and we're going to see more about that next chapter. By the way, take a look at that YouTube video that I posted last time. That's going to be really helpful. So finally, photons and electrons do this. Maybe everything does. And so, yeah, everything in the universe is a particle or a wave. I should say a particle and a wave. Feynman likes to say that it travels like a wave and it interacts like a particle. Think about this light hitting this metal, right? It travels like a wave. It sort of waves down to the metal. But then the electron either grabs a whole photon or not. And so it actually grabs the whole thing. It interacts like a particle. Now, radio waves have these really, really wimpy photons. You know, a single photon of radio waves is hardly anything. They have to come in bunches to do anything useful. As soon as you have bunches of photons, you might as well just call it a wave. Whereas a gamma ray, even a single gamma photon, can really wreak some havoc. And so you'd really consider that to be a particle. All right, I guess that's it.